look at population versus sample. This is a major, major hit in statistics. Sometimes when we take a survey and we look for answers to things, we need to get enough people to survey, enough objects to test. We can't always get the population because it's too big. If I wanted to ask every car dealer what's their gas mileage of their most economical car, I would have to go to every single car dealer across the United States. That would take probably until the next new car came out with a better gas mileage. Well, yeah, but we'd be doing this for a really long time. So what you do instead is you find a sample. And we're going to talk about sampling techniques. You want to get enough of a random sample. You never want it to be biased. You don't want to have a certain way that you're going to select this. And in this chapter, we're going to talk about that. But you're going to develop a random sample. And from that sample, which is hopefully a good size, you're going to make an inference about the population. So we have to take our sample, which is a subset of our population. This is your population, and you're going to just take a good sample. Sometimes you do more than one sample. Depends on the length and the depth of your study. You do more than one, and you take a look at all your samples, and we do a whole section on that, and we make an inference about our population. This is your inferential statistics. You have a descriptive part that describes the miles per gallon. Every car dealer submitted their best car miles per gallon. I got 32 miles per gallon, 45 miles per gallon, 52 miles per gallon. They all submitted their statistics for me, and then I compile it and I make an inference about the population. I go for the car that has the best gas mileages. Maybe I take the average. I take a look at it, and I make an inference. So in statistics, it's not always possible to find the population. 9 times out of 10, you don't find the population. So you have to do your samples. Now, here's just examples of statistics. And statistics is all around you. Every time you look at your baseball scores, your standings for the football leagues, any of that, those are statistics. Anything that's countable. How many people in this school? How many courses you take? What's your GPA? All of that. Those are all statistics. When you were younger and you went to your pediatrician, they said you were in a certain percentile based on your weight, based on your height. Those are statistics. So it's a little bit concerning if my child is a little bit under the normal birth weight, under the normal weight. I have to worry about that.
Do you have tape?
Yes.
I don't mean to interrupt.
You're fine. Yeah. You okay?
Oh yeah, fine. I just gotta tape something quick.
Oh, go ahead.
I'm good. You go back.
So statistics are everywhere that you look. That you're getting information from. And that's okay. And you generally believe your statistics, like we looked at that article. You generally believe your statistics rather than someone saying, this is the best car, buy this car, this is the best car, and you say, why? So Consumer Reports has all the statistics on that car, showing you why that's the best car. So these are just nice examples, and these are from the book. I copy as much as I can from the book to go over it with you in class. So women who smoked 1 to 14 cigarettes daily had nearly 2 times the risk of sudden cardiac death as their non-smoking partners. Now, what's nice about your book also is it usually, 99% of the time, gives you a source. This source was taken from the American Heart Association. This is a proven statistic. They did their research. It's kind of vague here from 1 to 14, but that's saying any woman that smokes automatically has a 2 times the chance of having sudden cardiac death as someone that doesn't smoke. Not counting second-hand smoke. You got to kind of keep it confined. Another example of a statistic, food waste in the United States has progressively increased from about 30% of the available food supply since 1974 to almost 40% in recent years. That's the food we waste. And this was taken from another source. So statistics are your way of gathering your data, collecting it. I hope that doesn't slam. Collecting it, interpreting your data, and making your decisions. This is the important part. This is why you collect your statistics. You want to make a decision based on that. And you look at your team standings. You're looking to see who do you think is possible to win your baseball leagues. So you go look at their statistics. Who's got the most wins? Who's got the most losses? You don't want to pick them. What pitchers are pitching? What are their ERAs? What are your statistics? That'll help you make a decision on which team do I think is going to win this year. I'm going to look at what their records are. I'm going to look at their statistics. So those are the things we look for in your statistics. And basically, we look at two types of data sets. Your population, the big one, versus your sample. Now, even though we call these statistics, a statistic is really related to a sample. In other words, if I say 14% of all men in the United States went to college, okay, and we still say that's a statistic. If it's about the population of all men, it should really be a parameter, but we still call it a statistic. But statistics are technically from your sample, and parameters are from your populations. The census does all population, and they have even changed their ways to do things. Every 10 years, a census is done, because it pretty much takes them 10 years to compile all that information that they collected. And they start with sending you packets home to fill out, then they make phone calls, and they district them, so that each district is calling their own people, trying to get them to send in their information. And it's not against the law not to send it in. So, usually somebody will say, somebody's going to follow up on this, but it doesn't mean you're being arrested if you don't send it in. So you don't always get all your outcomes and your responses that you're looking for. So sampling is mostly used when we collect data. Most of this first chapter is a lot of definitions. And the hardest part is figuring out what is my sample, what is my population. Now, when we do this, you always look at the number they give you and you say, are there more? If there's more, then this is a sample and it comes from your population. So in the first example, in a recent survey, 614 small business owners in the United States were asked whether they thought that their company's Facebook presence was valuable. 258 of those 614 said yes. So first we look at, what is this 614? Population or sample? Sample. We say, are there more than 614 small business owners? So this is my sample. My population is all small business owners in the United States. So I took a random sample selection. I looked at all the population of small business owners, and I took a specific 614 of them. Yeah. No, but these are just examples that come from your book. So, do the examples with me. I try to give you enough notes to cover, but the examples, you might want to write in your notebooks. This is if you were looking at your book right now. This is right from your book. Rachel has a good point, guys. This is like right from your book. So if you want to write anything down, feel free. If you're fine with it, then we go through it. Now, your sample data set comes from your sample. You started with 614 small business owners. Of them, 258 said yes, and then the rest said no. So 614 minus 258, they said no. That's your statistic. That's a statistic on this. That 58% said yes. This is your statistic. It is not part of your sample or your population. Your sample is your 614. Your population is all small business owners. Okay? All right, now you're going to try the next one. You're going to try the one on the bottom. The U.S. Department of Energy conducts weekly surveys of approximately 800 gas stations to find their approximate average gas price. On December of 2012, the average price was $3.35 per gallon. I want you to identify the population and the sample and tell me the statistic that they give. This is the difference from the new book to the old book. The old book, it was $1.37 a gallon. That's how old that old book is. Yeah, just jot it down and then, Nick, do you know what your sample is? Okay, what's your population? All gas stations, where? Uh-huh. They don't tell us where, but what can you figure out?
In the U.S.?
United States, because who's doing this?
U.S. Department of Energy.
Yeah, so all gas stations in the U.S., and what's your sample? 800 of these gas stations, and what's our statistic? Average price is $3.35 per gallon. This is a statistic because it's based on your sample. Good. See it? It's not so bad in the beginning. Okay, we're going to describe if this is a parameter or a statistic. It's kind of nice because statistic is S, sample is S. Population is P, parameter is P. So they pair together. So the first thing we have to decide is, are they talking about a sample or are they talking about a population? A recent survey of approximately 400,000 employers reported that the average starting salary for marketing majors is $53,400. Is this a sample? So if this is a sample, is it a statistic or a parameter? It's a statistic. Good. Okay. The freshman class at a university has an average SAT score of 514. Parameter, how did you know this was the population? It's the whole freshman class. So that's a population, so therefore it's a parameter. Even though we say statistic, we say the statistic is that they have an average of 514, it's technically a parameter. You hear that very few times. In a random check of 400 retail stores, the Food and Drug Administration reported 34% of the stores were not storing fish at the proper temperatures. Sample and statistic. Good. Because we say, are there more than this many stores? Yes, Oliver.
It will always be a sample, statistic, or a population.
And it will always be a sample and a statistic, a population, and a parameter. PPSS. They pair. But what I was saying before was, you hardly see the word, people hardly say, oh, this is the parameter. They usually say, this is the statistic. So it's kind of like lumped under the word statistics because this statistics is technically defined as any collection of your data, any numbering of things. So it kind of has a little bit of overlap there. Technically, it is a parameter. But we say statistic because the actual part is collecting your data. So you guys take a minute and try this. Okay? Think about it for a minute. Does the company have more than that employees?
No.
No. So if this is all the employees that that company has, then it's a population. A company with 65 employees spent a total of over $5 million on their employee salaries. So you say to yourself, are there more employees in that company? No, that's the population for that company. So therefore, this piece right here is a parameter. Okay? We say, are there more? That's the key. Take whatever number they give you and say, are there more? If it's for a specific company, for a specific class, for something specific, and they usually say the, like Nick pointed out before, it said the. So, that's how you can usually tell, or do they have anything else? Okay. Another set of definitions is just the two branches of statistics. And we cover both. Descriptive statistics is what we're just looking at. 54% of companies voted yes on the new energy bill. Those are your descriptive statistics. Question? No? What you do with them is called an inference. So if I'm wondering what people think of Obama's speech last night, anybody watch Obama's speech? About the you had to for government? Yeah. Okay, good. So, you all watched it. Okay. Oh, okay, so maybe I won't use that example. Alright, so he came out with some statistics in his speech, right? And now we have to infer what we think is going to happen from all this. So we get the background, the statistics of something, and then you make an inference. And generally, you sample, you find your statistic, and you make an inference. Okay, so I'm looking at this. I say, last year, this is just made up, 67% of all high school students went to college. That's my statistic. Is it a population or a parameter? I'm sorry, is it a parameter or a statistic? 67% of all high school graduates, population. I call it my statistic because it's still the gathering of information. There's kind of a little overlap, but technically it's a parameter. Now, I need to make an inference. What's one thing you can infer? What's one thing that you can say from that?
More than half college.
Good. More than half of our high school students are going to college. In fact, it's almost close to 3/4 if you think about it, right? 67 is close to 75. So there's your inference. Is that good? So I'm thinking, is this good? So as a college, as the dean of a college, how should I look at this? How should I look at this? Well, 67% are coming out of high school going into college. It's a little more than half, a little less than 3/4, somewhere in between there. So shouldn't I get more people coming to my college? Shouldn't I maybe prepare myself for a better enrollment next year? Maybe put my college out there, make it known a little bit more? Brace myself for this? If I'm a high school guidance counselor, or if I'm a high school superintendent, let's say I'm a superintendent of a school, is 67% good? No, I want that percentage to be higher. From a college point of view, they're thinking, oh yeah, it's increasing, it's getting higher. From a superintendent's point of view, I want that to be higher. I want to up my standards. I want to up the rigor of your work, which is what we're all in the process of now, upping the rigor of things to get more people into college. So when you deal with this, your inference depends on what side of the coin you're looking at. One is, yeah, that's a good amount. I need to brace my college for more students coming in. The other is, hey, I need to get more graduating up here. I need to get more to go to college, right? So those are things that you infer. Example 3. A large sample of men aged 48 was studied for 18 years. For unmarried men, approximately 7% were alive at 65. For married men, 90% were alive at 55. What's the descriptive part of this statement? Damani? Okay, that's our sample here. This is our sample. Our sample is a large sample from the population of all men. But what do we say about this group? And what did we come out with as a result of it? And what is it? What would be your stick? Keep going. Keep reading. 70% for unmarried men. 70% for unmarried men are alive at age 65. This is a statistic. This is a descriptive statistic. It describes something about what you just did the study on. What's another part? The 90%. For married men, 90%. This is also a descriptive statistic. This is describing something that resulted from my study. Can someone give me an inference about this? Come on.
The men who are married were alive. More men that were married stayed alive at age 65.
And why do you think that is? Well, let's make an inference.
I think it's kids.
Okay, maybe suicide rate. That's a good inference. Maybe unmarried, they were upset not being married. A little depression. That's a good one. Yeah, they drank more. That's why they were not married.
And they don't have someone to take care of them, probably.
They don't have someone to take care of them. Behind every man is a better woman. Type deal.
No kids.
No kids. No kids to keep them going, to keep them alive and going. Right? Yeah, I mean, do we know that any of that is true? No, but that's an inference that we make. That's an inference.
Oh, they could be unmarried with like 50 baby moms.
Yeah. Okay.
That's too much child support. That's what it's like.
Hang on, guys. One more. Hang on, one more. In a sample of Wall Street analysts, the percentage who incorrectly forecasted high-tech earnings in a recent year was 44%. What's the descriptive statistic? Oliver.
Wall Street analyst.
This is your sample. That's your sample. What describes what happens with this? The high-tech earnings was 44. Was incorrectly forecasted in a recent year was 44%. Okay, that's the descriptive statistic. And an inference might be that's pretty high for incorrectly forecasting their earnings. Maybe their earnings are hard to find. Maybe they work more on commission and it's not reported. Maybe there are hidden things out there. We can't find them that easily. So those are things we look at.